So in this video, I want to go over the answers to the questions in activity 1-1. So the first question is question 1-1, and there are two loops of wire shown. One that looks like this, which has an X and a dot, and one that looks like this. That has current going into the page up top and out of the page down the bottom. Okay, so this is a loop of wire with current coming up and out and then down and in as it goes around in that way. So if I use my right-hand rule to figure out the direction of the magnetic field for this loop of wire, here's my loop of wire. I can take my, let me zoom out a little bit. I can take my thumb and put it out of the page on this side, and I see that the current is coming out of the page and then back into the page, and my fingers are pointing down this way in the middle of the wire. So what I can say is that B points down like that. Okay, so this is, I'm going to try and show you with this video and a kind of easier way to think about a loop of wire, because we're going to, in this lab, have forces that are exerted on this wire that are going to cause it to rotate. And when we did this in class, we talked about these forces as being due to right-hand rule 2, or the right-hand rule where the current is your hand, your fingers point in the direction of the magnetic field, and your thumb points in the direction of the force. But we can also think about this as being a magnet. So I have magnetic, we can think about this as being a disk magnet with the North Pole down here and the South Pole up here. Right, magnetic North Poles always point, or sorry, magnetic field lines always point out of North Poles and into South Poles, like that. So now we can think about it, this is just being a magnet. So if this North Pole is near another North Pole, there will be a repulsive force. If this South Pole is near another South Pole, there will be a repulsive force. This is going to be a shorthand for doing that, but we have to kind of get a feel for what this looks like first. So I can do the same thing here. And if I do the same thing here with my right-hand rule, I'll get that the magnetic field looks like that, which means this is the North Pole and this is the South Pole of this magnet. And I'm going to call it an electromagnet because this is a magnet generated by a current carrying wire. Okay, so I think in this question I said stare at this and memorize it. So if you can imagine, sort of, it goes out, north, in, out, north, in. This sort of configuration. No matter how I spin this thing, and your loop of wire does most certainly spin, that's what's going to be happening in this lab. We can still think about, right, the North Pole being the one that has the dot on this side and the X on that side. Okay, so now let's go ahead and answer the parts for question 1-2. So the first one is that I had the North Pole of a magnet down here. So this is like a strong disk magnet with a north up here and a south down here. Would probably have been a better way to draw that, but it kind of got written with a North Pole, so there's a North Pole on the top. Okay, and now I have a loop that looks like that, and current is coming out of the page and then back into the page. And you can look up here and sort of just imagine all this has to happen is for this loop of wire to rotate a little bit, and it'll turn into this loop of wire. So I can think about this being the North Pole of a magnet and this being the South Pole of a magnet. So in the lab, all that this loop of wire is going to be able to do is spin. It's not going to, right, we have a North Pole next to a North Pole. So what this loop of wire would want to do maybe is to move up, to move away. But that's not what it can do. What it can do, though, is rotate a little bit. And I think maybe, hopefully, if you convince yourself by staring at this hard enough, you could maybe convince yourself that the way that this is going to rotate is that way. Another way to think about this, which is a longer way, but one that is probably more familiar to you, is to use the right-hand rule. So let's use our right-hand rules and make sure that this works. So I have the north pole of a magnet is creating an external magnetic field. So magnetic field lines always point out of north poles. And so let's use the right-hand rule to figure out the force that would exist for a current carrying wire with current coming out of the page in the presence of an external magnetic field that it did not create going up. So I will use the right-hand rule with my hand. So my right hand, the current comes out of the page, the magnetic field points up to the top of the page, and my thumb points to the left. Okay, so there would be a force right here that points to the left, a magnetic force. I can do the same thing over here, where now the current is going into the page. So I'll do my hand like that. I turn my hand so that the magnetic field can point up, and now the force points to the right. All right, so zoom back in on this. Now we have these two blue arrows that we got from using the right-hand rule that tell us that this loop of wire is going to rotate counterclockwise. But hopefully you were able to just intuit by knowing that this was the north pole of the magnet, that we already knew that this loop of wire was going to rotate counterclockwise like that. So the green arrows, which we got just from our intuition about north poles repelling each other, told us the same thing that the right-hand rule did. If we move on to the next one, I'll say that I have the north pole here and a loop of wire like that. There's a dot and an X. So it always goes dot. Oh geez. I believe the magnetic field points this way. I'm going to look it up just to make sure I don't make a mistake on the video. Well, it's backwards anyway, so I guess we won't. Right, it comes out, it goes like that. Yeah, that looks good. So this is the north pole of my electromagnet, and this is the south pole of my electromagnet. And so there's going to be repulsive forces over here and attractive forces over here, and actually this will cancel out. So there is no net force. Well, and rather than a force, I'm going to call it no net torque. Torques are forces that cause something to rotate. So, and we're mostly interested in torques here, right? Things that will cause something to spin. So there's no net force on this wire either, but those two forces being oriented the way that they are will cause us to rotate. Oh, I didn't say that very well. So we already used our right-hand rule here to say that there's a dot out of the page has a force to the left. So I don't actually need to redo much in a right-hand rule kind of a way. If I imagine that the north pole of this magnet has a magnetic force or has a magnetic field that points up and out of the north pole, it goes like that. So right here I have a current coming out of the wire and a magnetic field that points up, and I know that it'll experience a force to the left. Here is current going into the page in the presence of a magnetic field that points up, and I already figured out that that will experience a force to the right. So this is going to rotate counterclockwise, just like that. And as it rotates counterclockwise, that is what's going to happen. So we could also have figured this out from the fact that north poles will repel. So we have a repulsive force over here and an attractive force over here. So we're going to sort of be repelled, that way and attracted that way. And that also is that I've drawn my arrows in a way that looks like this whole thing is going to rotate counterclockwise as well. Okay, last but not least is this third one. Pull that up on the screen. So it looks like this. I have the north pole of the magnet looks like that, and X's and dots. And I can again know that the magnetic field points up out of the north pole of our strong permanent disk magnet. And without doing this sort of north-south pole thing just yet, we already know that out of the page experiences force to the left, into the page experiences a force to the right. So these two forces aren't going to cause any sort of rotation. So this one, not that one, but this one over here is no net torque. I can also use my magnet trick, which is that, and actually if you look, these two are coils oriented exactly the same way. So down here is the north pole of the magnet, up here is the south pole of this magnet. And we have north next to north, so it will repel and it'll experience a force that's trying to move it up, but it experiences the same force on both sides of this, so it's not going to rotate. Okay, so for the case, the second part of question 1-2 says, for the cases in the previous question, when the loop does spin, does the loop spin indefinitely? And the answer to this is no, it doesn't actually spin indefinitely. They will spin, so this one here is going to spin until it ends up like that. So this is going to continue to spin, so it's here. So let's take this one. A short time later, it's going to rotate counterclockwise, so the dot's going to be up here, and the X is going to be down here. And the north pole will be here, and the south pole will be here. After that, it's gonna, and then we'll have a force out of the page points to the left, a force into the page points to the right. So this will continue to rotate. But kind of eventually it's going to end up so that the dot becomes here and the X rotates all the way to here. So eventually it's going to look like this with a dot and an X in our loop. And now a force will be to the left for this, for the out of the page, and we'll have a force to the right for the current that goes into the page. And now we see that the force is acting to try to pull this apart, but it's not acting to rotate it. So eventually this one is going to end up here, and then it's just going to get stuck there. So what eventually is going to happen is if this thing starts like this, it's going to rotate around, and it's going to kind of go boing, a boing, a boing, a boing, a boing, a boing, a boing, and it's just going to get stuck. And actually, if you have some unlucky choices on how you stripped your wires, you might end up with a motor that only does that. It has a very strong preference to be oriented in one way, but it doesn't rotate. So if you did that, it's this is why that happened. This is also why you don't want current flowing all of the time. What you want now is for when you get like this, for the current to turn off so that your coil can keep rotating for a little while. But that might make a little more sense later on in this lab than right in the very beginning. So I'll leave it to you on this one to figure out exactly how this one ends up. And this one is, of course, not rotating in the beginning, so it will never start to rotate.